In this lecture, we'll lay the groundwork for using Python in data-driven problem solving. Python is one of the most popular and accessible programming languages today, and it plays a central role in modern data science. Whether you're just beginning your journey in programming or building toward applied machine learning, the topics we cover here will form a foundation for more advanced work. We'll explore not only the syntax and behavior of Python itself, but also how it connects to powerful data science libraries and tools. These concepts are essential for anyone looking to analyze data, build reproducible code workflows, or visualize trends. By combining core programming concepts with hands-on tools, this course aims to build your confidence in writing clean, efficient Python code and applying it to real-world data tasks. Foundations of Python and Tools for Data Science by the Programming Professor. Here's a quick overview of what we'll cover in this presentation. We'll begin with an introduction to Python and Jupyter, explaining what makes Python ideal for data science and why Jupyter Notebooks have become a go-to environment for coding and documentation. From there, we'll examine Python data types, including built-in types and container structures, before moving into functions and variable scope. Next, we'll explore how to work with data science packages, learning how to import and use powerful tools like NumPy, pandas, and matplotlib. These packages form the backbone of numerical computation, data manipulation, and visualization in Python. Each section of this presentation is designed to help you write better code, understand your data more deeply, and communicate insights more effectively. By the end, you'll be able to move fluently between core Python syntax and the tools used by data professionals in the field. Python is an open-source programming language that's widely used in data science because of its readability, versatility, and extensive library ecosystem. It was developed in the late 1980s and officially released in 1994. In 2008, Python 3.0 introduced major improvements in syntax and structure, although it wasn't backward compatible with Python 2. One of Python's biggest strengths is that it's open source, which means anyone can contribute to its development by creating new libraries or extending functionality. This has led to rapid growth in tools for everything from web development to artificial intelligence. On the plus side, Python is known for its readable code, strong community support, and constant innovation. However, there are trade-offs. Some users encounter inconsistencies between libraries, and Python generally uses more memory and runs slower than lower-level languages like C or more performance-optimized languages like Julia. Despite these limitations, Python remains one of the most accessible and powerful programming languages in the world today. At its core, a Python program is a sequence of instructions executed line by line. A key concept in programming is the variable, which stores a value using the equals assignment operator. An expression is any line of code that evaluates to a value. Together, variables and expressions form the building blocks of computation in Python. When you write code, it is interpreted and translated into machine instructions by the Python interpreter. Typically, you write code inside an IDE, an integrated development environment, which makes it easier to run, test, and debug your programs. A simple example might involve storing temperature predictions and calculating the difference between predicted and actual values. These variables can be reused and updated as needed, enabling the development of dynamic and interactive programs. Understanding how variables and expressions work will allow you to write more meaningful code as we move into data manipulation and function design later in the course. Functions in Python allow you to organize code into reusable blocks that perform specific tasks. A function is defined using the def keyword, followed by a name, parameters inside parentheses, and a colon to begin the indented function body. Parameters are variables used inside the function definition, and when the function is called, values passed into it are called arguments. Functions may return results using the return keyword. Some functions produce visible outputs like plots, while others may silently perform calculations or update data structures. For example, you might write a function to estimate travel time based on traffic levels, with different outputs depending on the input. By wrapping this logic in a function, you avoid repetition and improve code clarity. Functions play a vital role in structuring programs, enabling you to break down complex problems into manageable steps and reuse solutions across different parts of a project. Jupyter Notebooks are a widely used development environment in data science, known for their ability to combine live code, visual output, and explanatory text in one interactive interface. Originally part of the IPython project, Jupyter now supports many programming languages, but it remains most popular with Python. One of its main advantages is that you can run code in small, manageable cells and immediately see the results. This makes it ideal for experimenting with data, testing code snippets, and building reproducible workflows. You can also use Markdown cells to include formatted text, equations, and documentation, making Jupyter Notebooks not just a coding environment, but also a communication tool. Whether you're conducting an analysis, preparing a tutorial, or sharing your findings, Jupyter allows you to combine all parts of the process, code, explanation, and output, into a single, easy-to-follow narrative. Python includes several built-in container types that are essential for storing and organizing data. A container holds multiple elements and can vary in terms of whether it is ordered, indexed, and mutable. The four most common container types are lists, tuples, sets, and dictionaries. Lists are ordered, indexed, and mutable, ideal for flexible data storage. Tuples are similar but immutable, meaning once they're created, their contents can't change. Sets are unordered and unindexed but mutable, and they automatically remove duplicate values. Dictionaries store key-value pairs, are mutable, and ordered in recent Python versions. Each container type is useful in different contexts. For instance, you might use a list to collect values from a loop, a tuple to store constant coordinates, a set to find unique entries, and a dictionary to associate labels with values. Understanding these types will allow you to choose the right data structure for the task at hand and write more efficient, readable code. Let's take a closer look at lists, one of the most commonly used container types in Python. A list is created using square brackets and can contain elements of any data type, including numbers, strings, and even other lists. Lists are ordered and indexed, which means each element has a position you can access using bracket notation. Lists are also mutable, so you can change, add, or remove elements after the list is created. For example, you can update an element using list0 equals new value, add new elements with append, or remove items with pop or remove. Python also supports built-in functions like len to get the list length and operators like plus to concatenate two lists. Lists are ideal for situations where you need to store a sequence of items that may change, such as user input, dynamic results, or collections of data being processed in a loop. Mastering lists is key to effective data handling in Python. Tuples are similar to lists in that they are ordered and indexed, but the key difference is that tuples are immutable. Once created, their contents cannot be changed. Tuples are defined using parentheses instead of square brackets and are often used when you want to group values together that should remain constant. For example, coordinates or RGB color values are commonly stored as tuples. Although you can't change individual elements, you can concatenate tuples or create new ones by combining them. Python also supports named tuples using the collections.nameTuple class, which allows you to access tuple elements by name as well as by index. This can make your code more readable, especially when working with structured records like points, events, or database rows. Because of their immutability, tuples are more memory efficient and slightly faster than lists, making them a good choice for fixed-size collections where data integrity matters. A set is another type of container in Python, designed to store unordered, unindexed, and mutable collections of unique items. Sets are created using curly braces or the set function and automatically remove duplicate values. Since they are unordered and unindexed, you can't access elements by position like you would with a list or tuple. However, sets support powerful operations that are useful in many data science tasks, including union, intersection, and set comparisons. These operations allow you to efficiently compare groups of data, find common elements, or identify differences. For example, a set can quickly tell you which users appeared in one dataset but not another. Sets also support methods like add to insert a value and remove to delete one. Because of their automatic deduplication and fast membership testing, sets are especially useful when dealing with large datasets where uniqueness and fast lookups are important. A dictionary, or dict, stores data as key-value pairs, making it one of the most powerful and flexible container types in Python. Each key must be unique, and it maps directly to a value which can be of any type. Dictionaries are mutable, and starting in Python 3.7, they maintain the order in which items were added. You can create a dictionary using curly braces with colons separating keys and values, and access values using the key itself rather than an index. For example, grades LAX might return the test score for a specific airport code. You can update values, add new key-value pairs, or remove items using the del statement. Useful methods include keys to get all keys, values to get all values, and key in dict to check for the existence of a key. Dictionaries are ideal when you need fast lookups, structured data, or labeled associations, making them common in real-world data processing. Functions are fundamental to Python programming because they allow you to encapsulate logic into reusable modular blocks. There are two types of functions in Python: built-in functions like len and print, and user-defined functions that you create using the def keyword. A function definition starts with the header, containing the function name and parameters, followed by an indented block called the body. Parameters are placeholders for inputs, and when you call the function, those parameters receive actual arguments. If a function includes a return statement, it will pass back a value to the caller. Otherwise, it returns none by default. For instance, a simple function might take two numbers and return their sum. By wrapping logic in a function, you can reuse it across your program without rewriting the same code, making your code cleaner, more organized, and easier to test or update as your project grows. Understanding scope is essential when writing functions in Python. Scope determines where variables and function names are accessible in your code. Python has two main types of scope: local scope, which refers to names defined inside a function, and global scope, which refers to names defined outside of any function. Parameters are always local to the function in which they are defined. If you assign a value to a variable inside a function, it won't affect a variable with the same name outside that function, unless you explicitly declare it as global using the global keyword, which is generally discouraged because it can lead to unpredictable behavior. For example, defining a variable x equals 10 globally and x equals 5 locally inside a function will result in two separate values. Understanding how and where variables exist in memory ensures that your code behaves as expected, especially when dealing with larger programs or debugging complex functions. Python also allows for flexible function calls through keyword arguments and default parameters. With keyword arguments, you can specify which parameter you're assigning a value to, allowing function calls to be clearer and more readable. Default parameters provide fallback values for parameters if no argument is provided. These features are especially useful when functions have many parameters or when you want to make some arguments optional. For example, a function that calculates the volume of a pizza might have default values for diameter and height, but still allow you to override them when needed. Calling pizza volume would use the defaults, while calling pizza volume, pizza height equals 2.0, pizza diameter equals 10, lets you customize inputs using keywords. This kind of flexibility not only improves the clarity of your code, but also makes your functions more adaptable to different use cases without requiring multiple versions of the same logic. In Python, functions are not just blocks of reusable code, they are also objects. Like numbers, strings, and lists, functions have a type, a value, and a unique identity in memory. This means you can assign functions to variables, pass them as arguments to other functions, and even return them as values. The type of any function object is simply function. For example, if you define a function called greet and then assign it to a variable f, calling f will behave the same as calling greet. This concept is especially powerful in functional programming, where functions are treated as first-class citizens. It also forms the basis for advanced features like callbacks, decorators, and higher-order functions, which are common in libraries for data processing, visualization, and machine learning. Recognizing that functions are objects helps you write more flexible and modular code, especially when designing libraries or working with tools that rely on functional patterns. Python handles function arguments using a model called pass by assignment. This means that when you pass an object into a function, the function parameter is assigned a reference to the same object, not a copy of it. If the object is mutable, like a list, any changes made to it inside the function will affect the original object outside the function. On the other hand, immutable types like integers, floats, strings, and tuples cannot be modified in place, so any changes result in a new object. This behavior is critical to understand because it impacts how data flows through your code and whether changes persist after a function call. One important rule is to avoid using mutable types as default parameters, since they can retain changes across multiple function calls, leading to unexpected behavior. Knowing how assignment and mutability interact helps prevent bugs and ensures your functions behave consistently. To extend Python's functionality, you'll frequently use packages, which are collections of modules containing functions, classes, and other objects. You import packages using either import or from statements, and you can create aliases to simplify long names. For example, import pandas as PD is a common alias that shortens every reference to the pandas library. Once a package is imported, you use dot notation to access its contents, like calling pd.readcsv to load a data file using pandas. Packages allow you to build on existing tools rather than reinvent the wheel, which is essential in data science, where projects often require specialized tasks like statistical modeling, data cleaning, or visualization. Efficient use of packages is a core skill in Python, enabling you to integrate tested, optimized functionality directly into your workflow. Whether you're working with raw numbers or high-level machine learning models, packages make Python a highly extensible and practical language. To use packages that don't come built-in with Python, you'll need to install them using a package manager. A package manager handles the downloading, installation, and updating of packages, as well as managing dependencies, other packages that your package relies on to work. The two most common package managers in Python are pip and conda. Pip installs packages from the Python package index, PyPy, while conda is part of the Anaconda distribution, which is widely used in data science for its package management and environment control. To install a package, you simply use a terminal command like pip install pandas or conda install NumPy. These tools ensure you have the right versions of all required components and help maintain reproducibility across systems. Understanding how to install and manage packages is essential, especially when working on shared projects or deploying applications in environments where consistency and reliability are key. Let's review some of the most common data science packages used in Python. These libraries form the foundation of almost every modern data science workflow. NumPy, imported as NP, provides tools for fast, efficient numerical computation and underlies many other libraries. Pandas, imported as PD, offers powerful data structures for handling tabular and time series data. scikit-learn or sklearn is used for machine learning models and preprocessing tasks. For data visualization, matplotlib.pyplot, imported as PLT, and Seaborn, imported as SNS, provide plotting tools for both basic and advanced visualizations. Statistical modeling is supported by scipy.stats, sp.stats, and statsmodels SM, which allow for hypothesis testing and inference. In practice, most data science projects import at least 3 to 5 of these packages, depending on the complexity of the task. Familiarity with these tools not only accelerates your workflow, but also ensures you're using industry-standard methods that are widely supported and documented. NumPy arrays support multiple dimensions and are created using the np.array function. These arrays are of type indarray, and all elements must be of the same data type, which allows NumPy to perform fast and efficient computations. Arrays can be one-dimensional, two-dimensional, or higher, depending on how the data is structured. For instance, a 2D array might represent a table with rows and columns. You can access the shape of an array using .shape, which returns a tuple indicating the number of rows and columns. Accessing individual elements is done using bracket notation, such as A12 to access the element in the second row and third column. These arrays are essential for numerical tasks like statistical analysis, matrix algebra, and machine learning model input. NumPy arrays form the foundation of many other Python libraries, so understanding their structure and how to interact with them is key to mastering Python-based data science. NumPy provides a wide range of functions for working with arrays, especially when it comes to sorting, updating, or transforming their contents. These functions typically operate along a specified axis, which allows you to control the direction of the operation in multi-dimensional arrays. For example, in a 2D array, setting axis equals 0 will apply the function down each column, while axis equals 1 applies it across each row. The sort function is a good example. Sort array axis equals 1 will sort the values in each row individually. If you omit the axis or set it to none, the array will be flattened before the operation is applied. Many of these functions are available both as standalone functions and as methods attached to array objects, offering flexibility in syntax. The ability to operate along specific axes is critical when performing tasks like normalization, aggregation, or feature engineering, where understanding the structure of the data is just as important as the values themselves. NumPy also includes specialized functions for creating arrays from scratch, which is useful when initializing data structures or setting up test cases. The array function converts Python lists or other sequences into NumPy arrays and allows you to specify data type and dimensionality. The full function generates arrays of a specified shape, filled with a given value ideal for placeholders. The zeros function returns an array filled with zeros, while ones creates one filled with ones. Both accept a shape parameter and optionally a data type. For example, np.zeros of 3, 4 creates a 3 by 4 array of zeros. These functions streamline the setup process, allowing you to focus on logic and computation rather than manual data entry. Creating arrays programmatically is also a stepping stone to more advanced tasks like simulations, synthetic data generation, and performance testing of algorithms. In addition to creating arrays, NumPy provides tools for inserting, deleting, and sorting array elements. These operations help reshape or adjust arrays without starting from scratch. The delete function removes elements at specified indices along a given axis, while insert allows you to place new values into an array before a selected index. The sort function arranges values in ascending order, and you can choose the axis or flatten the array entirely for sorting. These functions are especially useful when cleaning data or preparing it for modeling, such as removing outliers, filling in missing values, or reordering features. Each function has parameters that control its behavior, making them adaptable to a variety of use cases. These operations are part of the reason NumPy is considered a powerful low-level tool in the data science stack. It gives you precise control over data structure and manipulation at a foundational level. Reshaping and flattening arrays is a common need when working with real-world datasets, especially when moving between file formats or preparing input for machine learning models. Reshaping changes the structure of an array without altering its data. For example, a 2D array with shape 2, 3 could be reshaped into a 3, 2 array, assuming the total number of elements stays the same. Flattening converts a multidimensional array into a 1D array and is often used when vectorizing data. NumPy supports different ordering conventions during reshaping. C order row major and F order column major, named after the C and Fortran programming languages. These determine the order in which elements are read into the new shape. Understanding how reshaping works is essential for aligning data correctly, whether you're loading it from external sources, preparing it for visualization, or feeding it into models that require specific input formats. NumPy includes several specialized shape manipulation functions that give you even more control over how arrays are structured. The ravel function flattens an array into a 1D array and defaults to row major order, but you can change the order by specifying F for column major. The reshape function transforms an array into a new shape while preserving its data, as long as the total number of elements stays the same. Unlike reshape, the resize function can actually change the number of elements by repeating or truncating values as needed. Another common tool is transpose, which flips the dimensions of an array, turning rows into columns and vice versa. This is especially useful when dealing with matrices or preparing data for operations that require a specific orientation. These shape functions are foundational in workflows involving data cleaning, feature engineering, and preparing input for machine learning models. Knowing how to reshape and reorient data allows you to adapt to the specific requirements of different tools and libraries. NumPy also provides a wide variety of math operators and functions for working with arrays. Basic arithmetic operators like plus, minus, asterisk, slash, and percent apply element-wise, meaning they operate on each pair of corresponding elements in the arrays. In addition to these, NumPy offers simple functions like sqrt, log, and sign that apply to each element individually. For summarizing data, you can use aggregate functions such as min, max, median, std, and var to return a single value based on the array's contents or across a specified axis. If you're working with linear algebra, NumPy includes matrix-specific operations like dot, matmul, and cross. Even scalar values are treated as zero-dimensional arrays in NumPy, which ensures that they are compatible with all these operations. These mathematical tools make NumPy a fast, reliable engine for numerical computation, powering many higher-level functions in data science workflows. Moving on to pandas, this library provides high-level data structures designed for handling labeled, structured datasets. The core structure in pandas is the data frame, which organizes data in a tabular format with rows and columns, similar to a spreadsheet or SQL table. In this context, rows represent observations or instances, while columns represent features or variables. Each row has an index, usually integers but customizable, and each column has a label, typically strings. One important distinction is that while each column must contain values of the same data type, different columns in the same data frame can hold different types, integers, floats, strings, and so on. This flexibility mirrors how real-world data is structured and makes data frames extremely useful for tasks like loading, cleaning, and analyzing data. Whether you're working with CSV files, APIs, or SQL queries, the data frame is your go-to structure in pandas for organizing and interacting with tabular data. Although NumPy arrays and pandas data frames share some similarities, they serve different purposes and offer different strengths. Both are indexed, ordered, and mutable, and both support multidimensional data with a dot-shape attribute. However, there are key differences. Arrays can have any number of dimensions, from scalars to high-dimensional tensors, while data frames are always two-dimensional. Arrays require a uniform data type for all elements, whereas data frames allow each column to have its own data type, which is much more representative of real-world datasets. Additionally, arrays use only integer-based indexing, while data frames support both label-based and integer-based indexing. This means you can refer to columns and rows by name as well as position. Data frames are especially valuable when working with messy, mixed-type data, where column labels and descriptive indexes improve readability and functionality. For most data science tasks involving tabular data, data frames are the preferred structure. Subsetting data is one of the most common and essential tasks in pandas. It allows you to access specific rows, columns, or values from a data frame based on labels, positions, or slices. To access a single column, you can use either df_column_name or df.column_name. To access multiple columns, pass a list of column names inside double brackets like df_name, population. When working by position, use .iloc to access rows and columns by index, such as df.iloc 0,1 or df.iloc 513. For label-based access, use .loc, which allows you to select rows and columns by their actual labels. An example would be df.loc 6, continent, population, which retrieves rows up to index 6 and 2 specific columns. Understanding slice notation is also critical. X:(y) means from x up to but not including y:(x) means up to x, and x:() means from x to the end. Mastering these indexing techniques gives you powerful, precise control over your data. Beyond selecting data by position or label, conditional subsetting allows you to filter rows based on specific conditions. In pandas, you can use comparison operators such as equals equals, not equals, greater than, less than, greater than or equals, and less than or equals to test values within a column. You can also combine multiple conditions using logical operators, ampersand for and, vertical bar for or, and tilde for not. These expressions return a Boolean mask, which pandas uses to select the matching rows. For example, country population greater than 100,000 will return only the rows where the population exceeds 100,000. You can also combine conditions, like selecting countries in Asia with a population over 250 million using country continent == Asia, and country population greater than 250 million. These conditional filters are incredibly powerful and allow for precise, readable queries without writing complex loops. They're essential for data exploration, cleaning, and analysis, especially when working with large or messy datasets where manual filtering is impractical. In addition to filtering, Pandas offers a wide range of methods for modifying and cleaning data frames. These include tools for accessing, inserting, dropping, sorting, and replacing data. The .at method retrieves a single value based on a row and column label. The drop method removes rows or columns, while drop duplicates removes repeated entries based on specified columns. If your dataset has missing values, drop_NA can remove them selectively, and replace can substitute specific values. You can also use insert to add a new column at a specified position, and sort values to sort the data frame by one or more columns. Each of these methods includes optional parameters like axis, in-place, or subset to control how the operation is applied. These functions make Pandas a comprehensive tool for cleaning raw data and preparing it for analysis or modeling, helping you avoid the common pitfalls of manual data wrangling. Data visualization is a critical part of the data science workflow, and matplotlib is the foundational library used for plotting in Python. It allows you to create a wide range of visualizations, from simple line graphs to complex multi-axis plots. Matplotlib works in different environments such as Python scripts, the terminal, and Jupyter Notebooks, and offers a high level of control over every element of a plot. Plots are structured around figures which can contain one or more axes, the individual plots, as well as components like ticks, labels, and legends. One of Matplotlib's major advantages is its customizability. You can control colors, fonts, spacing, and nearly every other aspect of a plot's appearance. It also has a syntax style that will feel familiar to users of MATLAB, making it easier to learn if you've used that environment before. Whether you're doing exploratory data analysis or preparing visuals for a presentation, Matplotlib is a reliable, flexible tool for producing clear, informative graphics. To get started with plotting, you typically import the pyplot module from Matplotlib, using import matplotlib.pyplot as PLT. Pyplot provides a state-based interface to build and manage plots, making it easy to stack commands for creating visualizations. The two most common functions are plt.plot x,y for line graphs and plt.scatter x,y for scatter plots. All plotting commands contribute to the current figure, which is displayed using plt.show. For example, if you define x equals 1, 2, 3, 4 and y equals 2, 4, 6, 8, calling plt.plot x, y will draw a straight line connecting those points. Matplotlib is designed so that you can build plots incrementally, adding more elements like titles, labels, and grid lines as needed. This structure gives you the ability to start simple and build up to more complex visualizations. Learning how to create and display basic plots is the first step in developing effective data graphics. Clear labeling is essential for making plots interpretable, and Matplotlib offers several functions to help with this. You can use plt.title to add a main title, and plt.xLabel and plt.ylabel to label each axis. These labels help users understand the context of the chart and what the values represent. Matplotlib also supports LaTeX-style math formatting, which is useful for displaying equations or technical symbols. You can add legends with plt.legend to explain what different lines or markers represent, especially useful when plotting multiple datasets. Additionally, you can use plt.annotate to place text at specific data points, helping draw attention to important features like peaks or anomalies. These annotations can include arrows, offsets, and custom text, making them highly adaptable. Adding proper titles, labels, and annotations ensures that your visualizations are not just visually appealing, but also meaningful and informative to the viewer. Matplotlib allows you to fully customize the style and appearance of your plots using either format strings or keyword arguments. Format strings offer a shorthand method to set the color, line style, and marker all at once. For example, RO creates a red plot with circle markers. Alternatively, you can use keyword arguments like color equals red, line style equals dash dash, and marker equals O to specify each element separately. There are many options available. Common colors include B for blue, G for green, and K for black. Marker styles include dots, circles, stars, and triangles, and line styles range from solid lines to dashed or dotted lines. If you omit the marker, only the line will appear. If you omit the line style, only the points will show. These styling tools give you control over how data is presented, making it easier to highlight important trends, differentiate between series, or match a specific design aesthetic in reports and presentations. Adding grid lines to a plot can greatly enhance its readability by helping users visually align data points with the axis ticks. In Matplotlib, you can use plt.grid to display grid lines, and you can customize their appearance with several optional parameters. You can control which axes the grid lines apply to X, Y, or both, as well as their color, line style, and width. For example, calling plt.grid, axis equals both, color equals blue, line style equals dash dash, line width equals 1 would produce dashed blue grid lines on both axes. Grid styles are not combined like line styles, so each attribute is specified separately. Grid lines are particularly helpful when plotting continuous data, or when you want to assist the viewer in estimating precise values. While they may not be necessary in every visualization, including them thoughtfully can make a plot more informative without overwhelming the viewer with unnecessary clutter. Matplotlib also supports multiple plots within a single figure, allowing you to compare different datasets or views side by side. This is done using the plt.subplot function, which divides the figure into a grid of subplots. The function takes 3 arguments: the number of rows, the number of columns, and the index of the subplot to activate. For example, plt.subplot 121 sets up a figure with 1 row and 2 columns and places the next plot in the first section. You can add additional plots by changing the index, such as plt.subplot 122 for the second plot. Once all plots are added, you can give the entire figure a shared title using plt.subtitle. This feature is particularly useful for creating compact, comparative visuals, like showing raw data next to a transformed version or comparing different models on the same data. Grouping related plots together improves clarity and helps tell a more complete story with your data. To wrap up, let's summarize the foundational concepts covered in this presentation. Python is a powerful open-source programming language that is especially well-suited for data science, thanks to its simplicity, flexibility, and extensive ecosystem of libraries. Jupyter Notebooks offer an interactive, reproducible coding environment ideal for both learning and professional work. Python supports a variety of core data types and containers, like lists, tuples, sets, and dictionaries, that allow for efficient data management. Functions in Python provide modularity and reusability, with support for scoping rules, default parameters, and even treating functions as objects. Key libraries like NumPy, pandas, and matplotlib form the foundation of most data workflows, supporting numerical operations, structured data manipulation, and visualization. With these tools and concepts, you're now equipped to start building Python-based data science projects, analyze real-world datasets, and communicate your findings effectively using code and visuals.
Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.